So let's put it all together. So this is again the protocol aspect. As we have seen before, for a protocol you need to cover what message to send. We call this the link state packet. So what information should it contain? What to do when you receive this link state packet? This is the action at a node. And when do you send these link state packets? These we call updates. So this is the information that is carried within a link state packet. So this packet should definitely contain the ID of the node that has generated this particular packet, not forwarded, generated the packet. And this should also include information about the link state of the node, that is the neighborhood information, the list of neighbors and the cost to each. Based on these two is how a given node generates the graph information. So this is necessary for calculating the routing. Lot of the other practical problems that we have seen are handled via the sequence number and time to live, which also needs to be carried as part of the link state packet. So what does a node do when it receives a link state packet? Let's look at it from the perspective of node X and node Y. Suppose node X were to receive a link state packet generated by node Y. Notice that Y need not be X's neighbor. It had come through some neighbor of X, but it was generated by someone else. So first thing the node X does is whether it had heard from Y before. Suppose it did not hear from Y before. What should it do? Basically, it needs to store the information because this is new information that it is getting. And as I mentioned earlier, it needs to time each of this entry. So it starts an aging timer. What if X had already heard from Y before? What should it do then? Then it should compare the sequence number of this new packet with the sequence number that is already stored. If the sequence number new is greater than sequence number old, what should the node do? Override the old link state information, refresh this aging timer and forward to the required neighbors. You don't have to forward to all, you will have to forward to subset of the neighbors depending on where you got this information from, like we talked about earlier. What if the sequence number new is less than the sequence number old? What should it do? You discard the received packets because you got some outdated information. So the next question is, when do you send these link state packet information? Notice that flooding leads to lot of traffic because this link state packet is sent to every node. So you should avoid flooding to the extent possible. Like before, whenever the link state information changes, you naturally need everyone else to know the information because the graph has changed. So in which case you have to flood. These are called triggered updates. We also need to support periodic updates. These need not be sent often because of this flooding issue, as I mentioned. In this particular case, you use very long timers of the order of hours. If you implement those three aspects of the protocol, each node now is going to get link state packet from every node and thereby it will have the complete graph information. Once you have this, you can use Dijkstra's algorithm to calculate the shortest paths to node and you're done. So here are a few points to note specific to link state algorithm. There is no problem of this count to infinity looping because each node has global information. However, it is possible to have transient loops when topology changed and you're in the process of getting the new topology information. Again, convergence in link state is very fast because you have global information. However, link state suffers from scalability problems because you are flooding the entire network and also the computation and the amount of information you have to store at each node is high because you have to maintain the entire graph information, which node has which neighbor, so on and so forth. So this flooding can be handled to some extent by setting periodic timers to hours. And this information is handled through the use of areas, which I will cover a bit later. Now is a good time for a break. Once you're back, we will cover a protocol called OSPF, which implements link state algorithm. OSPF, which stands for Open Shortest Path First, is a very widely used interior gateway protocol. You must be wondering, what is this interior? We will cover this shortly in an upcoming video, but for now, assume that this is a protocol that is used within a routing domain. This has more or less replaced RIP because it converges really fast. Unlike RIP, which operated at the application layer, OSPF operates at the network layer where the OSPF information, these link state packets, are encapsulated within IP datagrams with a protocol number of 89. So in other words, when this IP layer gets a packet, within the IP header, if you see that the protocol number is 89, you pass this to the OSPF process, which also operates at the network layer. Since I mentioned earlier that reliability is very important, so OSPF implements reliability itself via checksum as well as ACK mechanism. OSPF supports many features. Example, it supports authentication. That is, a router accepts messages from other routers only if it has authenticated those routers. This is very important to have. What if a malicious router advertised to other routers that it can reach all the IP prefixes in the internet at cost zero? What's going to happen? Everyone will start sending traffic here and it will just drop them, and that's it. Internet has been brought down. It also supports additional hierarchy. Remember, I said earlier scalability is an issue with link state. So it tries to make it scalable by introducing an additional level of hierarchy through areas. I will touch upon this briefly. It also supports load balancing, by which I mean if there are two equal cost paths to a given destination, it will try to load balance traffic along both paths. Again, this is feasible because you have global information about the entire topology. OSPF as such is a very complex protocol. It has many types of packets and a lot of action based on the type of packet. I'm going to provide a very high level overview. The relevant concepts we have already covered. So here is how OSPF handles scalability. The entire routing domain is divided into areas. So here we see area 0, area 1, area 2, area 3. Area 0 is a special area that is made up of the special area border routers. These area border routers basically interconnect non-backbone areas with the backbone area. Each area is definitely served by one area border router, sometimes even more. For example, area 2 is being served by two area border routers, this and this. It is easier to understand areas if we chart out the path taken by a packet. By a packet here, I mean IP datagram, not a link state packet. Suppose a host A in area 1 wants to send a packet to host B in area 3. The path taken by this packet is that it goes from this particular host to the area border router that is serving this particular area, and then it crosses the backbone. In this case, let's say it takes this path, and once it gets into area 3, again it finds out a path from this area border router that is serving area 3 all the way to the particular host. So how does this help scalability? Basically, the link state algorithm that is being run in an area, the advertisements do not leave the particular area. So for example, if this router is generating a link state packet, this is sent to all these routers and it is not sent to any other router. So the flooding happens only within an area. But then how do these routers within this area know how to reach other networks that are part of other areas? So this is handled by the area border routers. So what an area border router does is it is going to summarize whatever information it has learnt within an area by participating in the link state algorithm as part of the area, and it interjects this information into the other areas. For example, let's look at this area border router. So this area border router knows the topology of area 1. What it does then is it participates in the link state algorithm of area 2 as well as area 0. And when it participates, let's look at what it does in area 2. It generates a link state packet where it claims that it can reach all the networks that are part of area 1 at a cost of 0. So these other routers, if they want to send a packet to any network in area 1, know that they can reach it via this area border router. They don't know what the topology is within area 1, but they know how to reach particular packets in area 1. So this area border router does the same even within area 0 as well. That is how these other border area routers receive that information, and thereby they will summarize that information and inject it into their respective areas. Let me also mention this point where an area is served by two area border routers. So this will hear information, it is going to interject the area 1 information. Similarly, this also may have heard this information from this router and maybe via this router, so on and so forth, and it will also interject information about area 1. Now a router here may decide to go via this router or this router based on whatever is the shortest cost. In this particular case, maybe it makes sense for it to go via this area border router. Often when dealing with areas, the scalability becomes more important than the absolute shortest path. For example, if these two routers were indeed directly connected, you will not send packets over this path because according to this areas, this router will not advertise its link state information to this particular router. So that's with respect to areas. As long as you got a high level picture of how areas work, that's good enough. So here is the packet format of OSPF. All OSPF packets have a common header that is represented here. So the first field again is the version field. This, if you set it equal to 2, corresponds to OSPF version 2. There is in fact OSPF version 3 which handles IPv6. As mentioned earlier, there are many types of OSPF packets. So this specifies what is the type of packet. So there are packets called hello packets. For example, these packets are exchanged to discover other OSPF enabled routers. These packets also act as the keep alive messages so that you know if your neighbor has failed. So type 2 is a database descriptor packet. So they maintain databases. Let me not get into this. A router can request link state information from other router, that is done through request, and link state update is like a reply or a link state update that is generated periodically. As I mentioned earlier, acknowledgements have to be supported as part of OSPF, so this is the acknowledgement field. Following this is the packet length. It includes the header also, how big is the OSPF packet. Router ID is basically the generator of this particular OSPF packet. This is typically set to the IP address of the router. Remember, a router can have many interfaces and thereby many IP addresses. You can set it to the smallest IP address. To handle areas, these also specify the area ID. Checksum again I mentioned is important, so that's also included. And OSPF supports authentication. Within authentication itself, there are different types. Whether you want to do authentication, if you don't want to do, you can set it equal to 0. If it's a simple password authentication, or whether it's a cryptographic authentication. The field following this will carry some authentication information. For example, if it's a password authentication, you may specify some password information here. Following this is the message body, which varies depending upon what type of packet it is. So here is an example of a link state update packet. So this follows the header that I have described earlier. So here you specify the number of link state advertisement followed by the link state advertisements themselves. This link state advertisement itself has a header, and here is the header. This advertisement has an age. This corresponds to the TTL field as I have mentioned earlier. This link state advertisement itself can have different types, whether it is advertising a router reachability or whether it is advertising a network reachability, so on and so forth. And link state advertisement also has a link state ID who is advertising the sequence number that we have talked about, again a checksum, and the length of the packet and the body, which again is a function of type. All this is just to give you a flavor of how OSPF looks. I don't want to get into more details than that. Now that we have seen distance vector as well as link state, let's compare them both. In distance vector, each node talks only with its directly connected neighbors, but it tells everything it has learned. The problems we saw there are the formation of loops, the count to infinity problem, and the fact that this distance vector suffers from slow convergence. On the contrary, in linked state algorithm, each node talks to all the nodes but only states information about directly connected nodes. This, because you have global information, has very fast convergence, but it has scalability issues, which to some extent are handled via areas. So here is a summary. So linked state routing is another approach to routing based on reliable flooding. It provides very fast convergence, but it can pose some scalability problems. OSPF is a popular standard that implements linked state routing. Both RIP as well as OSPF fall under this category of interior gateway protocols. Up ahead, we will cover an exterior gateway protocol. This also goes by the name inter-domain routing.